Welcome to radar system course. We start a radar cluster here. So clutter is nothing but a unwanted echo because we we are getting the signal from the a target, that is the echo, but that echo signal is not provide information regarding the target, and that echo is called as the unwanted echo. So that unwanted echo that will be received at a radar. So unwanted radar echo. So we are getting the signal. So radar receiver receiving the echo signal from the different objects other than a target there. So that's why it is called as a clutter. So unwanted echo is called as a radar there. And this, because of this particular unwanted echo signal, so identification of target is very difficult. So, and we are not able to detect the target, we are not able to obtain the position of the given target there. So what do you mean by this unwanted echo? Unwanted echo is nothing but a clutter, and this unwanted echo occur because whatever the signal transmitted by the radar. So radar, suppose for example we have a radar present in a aircraft. So a echo signal received by the aircraft radar receiver. So that will receive the reflections from the land. Okay, so we can say that there will be the reflection from the land, means echo received from the land. Then we can say that echo received from the sea. Then we can say that we have the echo received from the rain. Then we can birds. Okay, so even it will be the insects also, or we have the whatever the terrain and all. Okay, so just like we can say that natural one, or we can say that trees and all. So we are getting the echo from the atmospheric conditions or atmospheric locations there. So maybe in atmospheric condition there may be the ionization takes place. Okay, so in the given particular atmospheric condition, so we are getting the signal because of that ionization happen in the atmospheric place there. So echo signal received at a radar means by a aircraft. So that will be from the land, sea, rain there. So these are all the components or these physical items present or available on a ground surface there. Okay, so we can say that echoes received from the land. On a land, there is a tree, something is a different heights of the terrain. If we are using a radar altimeter, so in that case, we are not able to identify a height properly because of the issues of a terrain there. So we are getting a different echo signal, other different echo signal other than the target, and because of that, we are not able to identify what is the target position, what is the location of a target, what is the motion of the target. All these are difficult. So that's why we need to know about what will be the a clutter present. So we need to remove this unwanted echo at a receiver, and that unwanted echo at a receiver that will degrade the signal to noise ratio. So we consider here a receiver. We are getting the signal from the receiver. That is about the unwanted signal. So we have a receiver now. Okay. Now at this receiver, whatever the unwanted signal we are getting, and due to that unwanted signal, the receiver is not able to detect whether that information belongs to target or not. So we need to remove whatever the echoes from this land, sea, okay, rain, birds, okay, likewise. So we are getting the echoes from those. So that will be removed by the radar there. So we need to design in such a way that we can remove this unwanted echo as well as the noise present at a receiver there, so that a signal to noise ratio will be improved. So if a noise is a larger, so then a signal to noise ratio will be reduced there. Then again issue occur regarding the receiver design, and we are not able to detect a target clearly there. So that's what we can say that a echo. We are saying that a land and sea, somewhere at a time of a rain there may be a cloud. Okay, so we are getting a different echoes from this a cloud also. We can say that a clouds also. Okay, that will be the part. Okay, so from the clouds we are getting the echo. Or if there will be the heavy rain, okay, again because of that heavy rain, so we are getting a echo from this heavy rain. So if a aircraft is used in air uh, used to measure the height and all, okay, or used to measure the any nearby target in that case, so this may be the echo. But if you consider in another way, so we need to develop a radar that will be measure the what will be the rain present there, what will be the clouds present there, okay, what will be the size of a terrain or not. Okay, so there are the different radars, and that radars are useful for the different purpose. Okay, so only that we are saying that radar is useful for identifying the target. So other than that, there are the remote sensing radar. They are measuring the what will be the sea level right now, whether there will be the tide or not. What will be the flooding position there? Okay, so that's what we are saying that a remote sensing radar. So what will be the clouds and all? So there are the different types of a radar. So in which we are measuring the rain, we are measuring the clouds, we are measuring the what will be the flood in the land. Okay, what will be the tide position in a sea there. So that in that particular case, whatever the echo signal received from the rain or a cloud, that not be a unwanted echo, because that radar is using that particular echo or a target or that signal received from the cloud. Okay, echo signal received from the cloud, and that is useful for the ground mapping. So whatever the flooding is there, what will be the rain, heavy rain, or what occurs there, or what about the cloud position, what will be the tide position, likewise what will be the terrain there. So that are again used for the mapping purpose. So radars are, we are saying a radar not only useful for identifying the target or a motion or a position. So again it will be useful for the measurement of a land, measurement of a the flooding position, measurement of a tide. Okay, other examples are there. But for our extent, so we need to know about for what purpose we are using a radar. So according to that, a unwanted echo is nothing but a clutter for that particular radar. So for measuring, if we are using a radar in a aircraft, so in that case, this one will be the unwanted echo for this receiver, radar receiver present in a aircraft. Okay, so likewise, we have a various echoes we are getting. So from that purpose, echoes we are receiving from the land or a sea, okay, that will be nothing but present on a surface. So that's why it is called as a surface clutter. So there are the types of a clutter. Okay, we can say that we are getting it two echoes. We are getting the echoes. So right now we are saying that we are getting the echoes. Echoes from what? Echoes from a surface. Okay, sorry. Echoes from what? We can say that a land or a sea. So when we are getting the echoes from land or a sea, so in that case, that echoes we are getting, that echo is called as a surface clutter. This one is called as a surface clutter. And if we are getting the echoes from what? Echoes from a rain or we can say that echoes from any atmospheric condition, that is ionization takes place. Okay, we have a atmospheric condition or atmospheric phenomena, we can say. Okay, in a atmospheric condition. So in that case, whatever the echoes we are receiving, that echo is called as a clutter, and that clutter is called as a volume clutter. Okay, this one is called as a volume clutter. We are differentiating a two clutter. One is from the surface, one is from the volume. Okay, there are the two types of a clutter there. And a radar getting the echoes from this land or sea or from this field. So what will be the portion of that particular land area? So in general, we are saying that whatever the echo received, okay, that is nothing but from the land, means the signal sent by the radar, there, there will be the reflection from the land. So right now, suppose I am saying that this one is about our a surface now, Earth surface now, and we have the a radar present in an aircraft. So now the signal sent here by this radar. So there may be the echo, there may be the reflection. Okay, there may be the reflection from this whatever surface there. So if it is a flat surface, so we are getting the directly reflection. If there will be the earth curvature, so reflection will be different. So in that case, we need to find out what will be the azimuth angle, or what will be the angle with the that makes with a vertical or a normal there. And that area, so what we can suppose to consider, so received, because a signal received from the given particular target. Suppose I am saying that there is a target here. So received signal from the given particular target. Okay, so that is about echo we are receiving. Then we can identify the target and all. Okay, so for example, I am saying that a radar is here. We have the radar antenna is present here. So now a signal is sent by the a radar to the aircraft, and then it will be received by the aircraft. So radar cross section means what will be the size of the target. So according to that, we are getting the signal. So in a case of a radar, we use a radar cross section. Okay, so what will be the area? But in in the clutter, we are getting the signal from the different objects present on a land or a sea. Okay, so according to that, we are saying instead of a radar cross section, we need to talk about that a radar density. Okay, so we can find out what will be the a surface clutter there. So surface clutter, okay, so surface clutter, that will be if depending upon that what will be the cross section per unit area. So you can say that a sigma 0 is equal to sigma c by a AC. Here is the sigma c is nothing but what? A radar cross section A, radar cross section, and this AC is nothing but the area. So we are getting the a surface clutter. So we can describe a volume clutter also. So volume clutter, that will be defined in terms of a ratio there, or we can say that in terms of reflectivity. So that will be is equal to sigma c by a VC. So sigma c here, because we are saying that it is about a volume clutter. So that's why a sigma c is nothing but what? A radar cross section. Sigma c is nothing but a radar cross section, and this VC is nothing but the volume. Okay, this one is what we can say that a radar cross section, and this one is nothing but the area. Similarly, we can say that, and this one is nothing but the a volume. So radar cross section from the given particular volume here. Okay, so we are getting a volume clutter, or we can find out the a surface clutter there. Now we need to obtain. So what will be the a surface clutter radar equation? Okay, so we can continue our discussion on a surface clutter radar equation. Surface clutter is nothing but the echo, unwanted echo. So we will see that what will be the a surface clutter radar equation. Okay. So now we need to know about what will be the a surface object. Surface means a flat surface. So we can say that this one is about a surface here, and in a aircraft we have a radar. Okay, so we can say that there is a radar in an aircraft. Okay, so we can say that we have a device here, and that this one is called as a radar now. Now, what happened here? So the radar is sending the signal to the a surface now. So this one is about what will be the illumination taken place from this radar. Okay, this is about the signal here, and then signal is reached at the surface, and that signal reach at a surface, so it makes an angle that will be a phi, and this angle is called as a grazing angle. Okay, this one is called as a phi, is called as a grazing angle. Now we generally say that a signal will be transmitted from this one, it will be reaches at a radar now, and from this we need to find out, so what will be the a position, or what will be the range from this radar. So we are getting a signal received from this a surface here, and we consider that a total area will be supposed to be AZ here. Okay, so we can already we have seen that a AC is nothing but what a clutter, for a clutter area. Okay, so instead of that, what will be the radar cross section there? For a radar cross section, clutter area will be AC here, and then from this we need to find out if what will be the a region of a clutter here. So this one is about a clutter region. From this, this one is called as a what, we can say that a different range. Okay, so already we have defined a c tau by a 2 here. Okay, so in that case that will be a tau is nothing but a pulse width, and that a c is nothing but what we are getting the a speed. Okay, so likewise, now from this a signal coming from the radar, we have a radar now, and a signal reaches at a given particular a surface now. So this, for a given particular surface, this particular region is called as a that this one is about a surface here. Okay, so this particular surface, from this there are some particular objects within, so that from this given particular element or a scattering element, through that a signal will be scattered to the radar, and for this it has a beam width of a theta v. So this one is about, from this radar we observe what will be the patch of the clutter here. Okay, so we will find out what will be the total patch of the clutter here, and we are saying that this one is about a c2 by 2, and this particular portion, this one is called as a 1 by 2 c2 sec of y. Okay, so this one is about a phi is nothing but a grazing angle. And this one is about a beam width here. Theta b is nothing but your azimuth beam width. Okay. So this one is a view. Okay. So from this aircraft, we are getting a signal. Okay. Aircraft echoes from this particular surface. That for a surface, it has the area of a AC here. So from this particular surface, so power received from the clutter. Okay. This one is about a clutter here. So that will be is equal to what? A C is equal to what? What will be the transmitted power by this radar? What will be the gain of a transmitting radar there? And then what will be the effective area? Then its cross section area we have. This one is about a sigma 3 here and a 4 pi bracket square raised to r raised to 4. Okay, that is will be the what? This one will be the a power received from the equator here. So this one is depending upon that what will be your a transmitting power. Okay, PT is nothing but what? A transmitted power. Then we have a GT is nothing but the gain of an antenna. PT is equal to what? Transmitted power by the transmitting antenna. GT is nothing but what? A gain of transmitting antenna. Okay, that AE nothing but equal to what? A effective aperture area of antenna. Okay, effective aperture area, and this R is nothing but the range here. R is equal to what? R is equal to range here. Okay, so R, we can say that R is equal to a range here, and this a sigma C is nothing but what? A clutter cross section. Clutter, a cross section. And this clutter cross section is sigma C. So we can have the equation of a C that is about PTGT. Now from this diagram, so if we calculate here, so what will be the from this equation here we need to calculate. So what will be the exactly the is clutter cross section. So sigma C here. This one is about a clutter cross section is equal to what? What will be the A area here earlier that we have seen sigma 0, then A area, a clutter cross section area, sigma 0, and AC is the clutter area. This one is equal to what? A sigma 0. Okay, so we can say that we have is equal to we have a sigma 0 here, then a range here, then we have a beam width theta b with a C2 by 2 here and a sake of a phi here. That is nothing but a sigma c. That is about a clutter cross section. Now, this is about a sigma 0 we can consider earlier. So that a sigma 0 we can say that a radar cross section density, this one r is nothing but the range, theta b is nothing but a azimuth beam width here. So for given particular signal we are getting C2, that is c is nothing but the velocity and t is nothing, tau is nothing but a pulse width here, and sec of phi, that is about a phi is about the a grazing angle. Then we can rewrite the equation, this one, this equation CTPTGT. So we can put here the sigma c and we can rewrite the equation, that is C is equal to what? APT GT. We can have the AE, effective area of aperture, and now we need to change here sigma 0 R theta B C2 by 2 and a 6 pi here. Divide by, we have this 4 pi square into R raised to a 4. Now this R get cancelled. This R here get cancelled. Okay, so this one is about the final equation. So if we write that R, so in this, instead of R raised to 4, there will be a R raised to a 3 here. So this one is about what? A echo received from the a surface clutter. Okay, echo received from the surface clutter, and that will be inversely proportional to a cube of the range here. Okay, so this one not depending upon the power, so it will be depending upon that a range here. So whatever the clutter we are receiving, that will be depending upon the a range here. So larger the range, okay, we can say that a clutter will changes here. Okay, so based on this, whatever the range we have, so according to that, a clutter power or echo received from the surface clutter or echo received from that unwanted echo received, that will be vary here. So then we know that what will be the signal power written from the target. Generally, we can say that a signal power is nothing but the S, and that will be written from the target defined with respect to the a cross section there. Okay, suppose we have a target. So what will be the signal power received from the given target? That will be is equal to what? Or we can write here PT GT. Then we have the effective area of an antenna, and then sigma T is nothing but a target cross section, sigma T, divided by 4 pi raised to R raised to a 4. Now this one is about here, and then we can say that this one is equation 1, this one is equation 2. So if we are taking a ratio of a signal to clutter F by C. Okay, so from this equation F by 3, then we are getting a S by C here is equal to what? What will be the a sigma T? Because PTGT get cancelled, AE get cancelled. Only we have the term what? A sigma T here. And we have the a term of what? Sigma 0, because R raised to 4 we are, so R will be here. We can say that a R, then a theta B, C 2 by 2 into a sec of a is 5. Now from this equation S by C, so we can find out what will be the maximum range. Okay, what will be the maximum range that will be used to obtain the minimum signal to clutter ratio. Okay, so we can find out here. So maximum range. Okay, what will be the maximum range? So that will be used to detect the minimum signal to clutter ratio, and from that we can find out a R max, and that will be nothing but the radar equation for this a maximum range. So it will be what? A sigma T by, we have a S by C here, that will be the ratio, and that S by C, in that case it will be a minimum one. Then as it is term sigma 0 theta B C2 by 2 here, and then a sec of phi. Okay, so this one we are getting a equation, and that will provide you what will be the a maximum range of a radar. So earlier we have discussed that a signal, whatever the signal we are receiving, that will be depending upon a what will be the a surface. Right now we are talking about for a given particular surface. This one is about a range equation. This one is about a range equation now. And that equation is depending upon that what will be the a clutter power there. Okay, so what will be the clutter power? So we are not consider here right now a noise. But if we say that a noise is there, so in that case, a clutter power, that clutter C is to be a larger than the what will be the receiver noise power. Then and then we can consider this equation R max with respect to that a signal to clutter ratio, and that will give us the radar range equation. So mostly a noise we can say that less than the a clutter. So for a given particular radar equation, so in that case we can say that maximum range of that maximum range is depending upon a clutter power, not with a noise power there. Okay, so R max is depending mostly on what will be the maximum clutter ratio, so that S by C will be a minimum. Okay, S by C will be minimum rather than the radar, whatever the noise power by the a receiver there. Then we say that we have a what will be the area. Okay, so clutter area. We need to talk about again a clutter area. What will be the theta b? What will be the azimuth beam width? What will be the angle from the radar? That is the incidence angle. Okay, and what will be the grazing angle? So based on that incidence angle and a grazing angle, so R max will be changes here. So for that purpose, whether we are using a what type of a radar, if we are using a altimeter here, okay, radar altimeter. So in that case, so grazing angle will be about a 90 degree. Okay, so then R max will be changes here, and for a different incidence of a signal, whether it will be a perpendicular or a parallel, or whether it has some angle. So according to that, a clutter power will be changed. So we can say that R max, so of that we can say that a C will be changed. So C will be depending upon a mostly what will be the a grazing angle, okay, and from this grazing angle we can calculate if a C here. So what will be the grazing angle? Grazing angle means what? From a radar, we have a radar signal here. From the radar, we can say that a signal will be reached at a surface, and this angle is called as a grazing angle. So now, if supposed to be radar is here, then there will be the a normal incidence. So instead of this one, so there will be the a normal incidence. So what will be the a incidence there? So according to that, a C will be a changes. Okay, so based on this C will be changed. So sine phi, or we can say that we are using a term a sec of phi here. That sec of phi will be a changes. So all these expressions we are talking about here for a clutter power and all, both are depending upon that what will be the a grazing angle. And we are saying that C will be more if we are increasing the power or a gain of an antenna. But everything is depending upon the a range here. Okay, so we are not interested in increasing the power, okay, or we can say that again. So everything is depending upon that what will be the grazing angle and what will be the a beam width. Okay, so that is about the azimuth beam width. So if that pulse, what will be the we are talking here? Okay, so that for the given particular signal, so that is about a 2. So if that pulse width will be a narrow, this flow will be narrow. If it is a small, then in that case, what happens? So it has a range will be a greater there. So ultimately, clutter power will be changed. So if there will be the long pulse, okay, then what happens? If there will be the pulse will be a long, then a signal to noise ratio will be increased there. Okay, so we need to see that while designing the radar here, whether we are using a long pulse or a small pulse, but a noise portion is to be lower because we are saying that a signal to clutter ratio is to be dominant than the what will be the noise power or a signal to noise ratio. So we use a compressed pulse, okay, so that a signal to noise ratio will be a low or a noise at a receiver will be low as compared to the a clutter power ratio. So signal to clutter ratio is to be a maximum as compared to the a signal to noise ratio. So we can use beam width or a that is about a pulse width to dominate the a signal to clutter ratio there. But a noise will be present at a IF here because we have a mixer stage, then we have a IF. So what will be the receiver noise at a IF? That receiver noise is depending upon the what will be the a bandwidth there. So at a receiver, what will be the a bandwidth there? So then noise will be introduced. But a clutter power, clutter or a clutter we are receiving, that will be a different. So noise probably will be low as compared to the a signal to a clutter ratio. Now, if we consider that, so there will be the a perpendicular incidence now. You can say that there will be the perpendicular incidence. So perpendicular incidence means what? We have a radar here and we can say that your antenna and then antenna will signal propagating the signal. This one is about a surface now. So this one is about a perpendicular incidence. So at a perpendicular incidence, that grazing angle phi will be what? It will be a 90 degree. So this one is about a phi will be of a 90 degree. So that's why if whatever the ratio we consider here, so that is about a antenna beam width, and we consider that a phi here. Okay, so earlier we have considered that is about the antenna beam width. So from this we can calculate what will be the a clutter area viewed by the a radar there. And that clutter area viewed by the radar that will be determined or that will be obtained from this grazing angle as well as the azimuth beam width there. We can say that rather than beam width azimuth beam, we can say that a antenna beam width. Okay, so in that case, what will be the area? So area AC is equal to a pi by 4 into r into theta b. Then we have r a pi b. Then we have a sine phi. So this pi is nothing but what? A grazing angle that will be a 90. And this factor pi by 4, because we are saying that the shape of that area will be elliptical, so that's why a pi by 4 is here. And we can say that a AC is nothing but what? Area. Okay. And then we consider that a G is equal to what? A pi square by theta b and a phi b. Theta b and a phi b will be the beam width, antenna beam width. Okay, we can say that this one is about a antenna beam width for the two different plane or a principal plane there. That's why theta b and a phi b now. And we can say that again, if we are substituting this AC and gain here, then a clutter equation, okay, after substitution, clutter equation will be what? Phi, we have a PT, we have a AE, then a sigma 0 by 6 4 R raised to 2 sine of a phi here. That will be the a clutter. So clutter power, if you see here, again it will be depending upon that what will be the range here. You can say that is C clutter power is inversely proportional to the a square of a range. So earlier equation we can say that clutter power that will be depending upon R raised to cube here. Okay, in that case, earlier case, because it has a grazing angle, not it will not be a 90 degree. Now the grazing angle is the 90 degree because it is a perpendicular incidence. So that's why a clutter power that will be C is inversely proportional to the a square of the a range. So signal received from the ground by the radar altimeter, that will be a C here, means we can say that C. And this equation that C is depending upon the what will be the position of a surface and all. So then we need to know about so what will be the a geometry of a surface clutter there, whether that there will be the incidence angle that will be perpendicular to the surface, and what will be the a grazing angle. Okay, so means incidence angle, incidence whether it will be perpendicular or whether it makes an angle that will be a phi. So that whatever the signal we are getting from the radar, okay, if we can say that a radar is here. So signal we are getting from the radar with an angle phi. So what will be this grazing angle? Whether that phi will be 90 degree or phi will be a below a 90 degree. So in that case, we can say that a incidence angle. Okay, what will be the incidence angle? So that will define or that will provide you the information regarding the clutter, and that surface clutter is mostly depending upon the incidence angle, or we can say that a diffraction angle, or we can say that with a grazing angle then. If the incidence angle is a normal to the surface, so in that case a grazing angle, that what we are saying, that will be 90 degree there, and in that case that grazing angle will be a tangent to the a surface here. Okay, so in that case, so depression angle that will be viewed from the local horizon. So that in that case it will be a perpendicular there. So instead of using a depression angle, so people are preferring a grazing angle to define a clutter power. So whether we have a surface, whether that what will be the geometry of surface, whether surface will be flat or a curved here. So if it is a flat surface, so we are getting the equation of a clutter power with this one. If a surface will be a curved one, if there will be the curvature, okay, so in that case, then that clutter power equation that will be it changes with the whatever the earth curvature is. For the given particular earth curvature, so we need to add a what will be the angle will make with a horizon. So just like we can say that the angle makes with a this particular local horizon, or if it will be the curvature, so what will be the angle makes with this particular horizontal tangent of this particular surface. So according to that, if phi will changes, so that a curvature, that clutter power will be changes there. So that's all about we say that regarding the radar clutter and their surface clutter radar equation. So with this, we stop here. So thank you.